Now let's talk about the activity of radioactive substance. And how can we define activity is basically this activity is symbolized as capital R. And it's basically the total number of nuclei distinguished per second. So this rate of rate of distinguishing the rate of distinguishing of the substance is known as the activity of the radioactive substance. And 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 we know the decay law. First of all, if I write down the decay law, and what's the decay law? Decay law is n naught e to the power of minus lambda t. Now if I differentiate this equation with respect to time, if I differentiate this equation with respect to time, what am I going to get is dn by dt is minus lambda n naught e to the power of minus lambda t. So dn by dt will be minus lambda n, because n is equal to n naught e to the power of minus lambda t. And this thing that we have, this is a rate of distinguishing. This dn by dt is my activity. This gives the measure of activity. And this activity can be written as, so I can write what I have dn by dt equals minus lambda n. So instead of this, I can write r. So this activity is, if I take the magnitude of this thing, this activity is lambda n. Now, this activity that we have here, it is certainly depending on the distinguishing constant or decay constant, and it is certainly dependent on the number of undecayed radioactive nuclei in the substance. Again, if I go again back to the equation that the decay law n0 e to the power of minus lambda t, if I multiply this equation by lambda, so multiplying both sides by lambda is going to give me lambda n equals lambda n naught e to the power of minus lambda t. And for this lambda n, what I have activity, so I can write r for it, and instead of lambda n naught, I can write r naught e to the power of minus lambda t. So this gives me the decay law in terms of activity. And what is activity? It is the rate of distinguishing of nuclei per second. So to move on from here, if I want to write this activity in terms of half-life, I can do that. I would like to write down this activity in terms of half-life. So what is activity now? Activity is lambda n. This is my activity, right? But lambda is 0.6931 by t half. So I can use this lambda in this equation, and I can write activity is n times 0.6931 by t half. And what we see here in simple terms, that this activity that we have, this activity is inversely proportional to the half-life. So if we have more half-life, then certainly the activity is going to be less, and vice versa. Now, talking about the units of this activity or radioactivity, and what units there are generally. If I talk about the SI unit, the SI unit of this radioactivity is becquerel. It is becquerel. It is becquerel, BQ, and this activity is said to be. The activity of a given sample is said to be 1 becquerel if it has 1 decay per second. So 1 becquerel means 1 decay per second with respect to a sample. And if we go back to some older units of activities, what we have, there are other additional units, but the older one is Curie. So this Curie, this 1 Curie, that is Ci, this 1 Curie is 3.7 times 10 to the power of 10 decays per second. So this is 1 Curie. And we can automatically say that this 1 Curie is 3.7 times 10 to the power of 10 becquerels. Okay. So there is another unit of activity, what's called as Rutherford. Rutherford. By the name of the person who discovered nucleus, and its symbol is RD. And what's this one Rutherford? One Rutherford is 10 to the power of 6 decays per second. So 1 Rutherford is 10 to the power of 6 becquerels. And we can have the dimensional formula for Becquerel, Curie, and Rutherford. That in all the cases it is the inverse of time. So if you want to know about its dimensional formula, it's m0 l0 t to the power of -1. It has to be like that. And the level of activity of a sample of a substance is directly proportional to the mass of the sample of the substance. So we have another important parameter here, what's called as instantaneous rate of change of activity. And this instantaneous rate of change of activity can also be calculated. And what is that? If I start with the decay law of activity, R equal to R naught e to the power of minus lambda t. And what I want to calculate is the instantaneous rate of change of this activity of a radioactive substance. So in doing so, what I have to do is I would like to differentiate it. I would like to differentiate this equation with respect to time. So what I'll have dr by dt is equal to what I'll have, it is r0 minus lambda will come down e to the power of minus lambda t. That should be the case. So what we have is we have r0, then we have minus lambda, that's the internal derivative of lambda t, and the same function that we have. Now if we go back with this, this is minus lambda, what is this? This is r. This is r. So dr by dt is minus lambda r. But we know that this r is lambda n. Activity is lambda n. So this dr by dt is minus lambda times lambda n. So this instantaneous, so this is r, the instantaneous change of activity is minus lambda square L. So we can see that this instantaneous change in activity is dependent on the square of the distinguishing constant. And we can also achieve the dependence of this this instantaneous rate of change of activity in terms of half-life, and that can be done by substituting the value for lambda square. So for lambda square we will have 0.6931 by t half whole square. So if we use that thing here and take only magnitude, then this dr by dt will be proportional to 1 by t square half. So what we find here is that the instantaneous rate of change of activity is activity of a radioactive substance is proportional. It's inversely proportional to the square of half-life.